Hello everyone present here, respected Professor Dr. Pius Augustine and my dear colleagues. Today, we the members of Group 9 of Chemistry Department, Sacred Heart College, Thevara, are going to present a presentation on the topic radiocarbon dating. Let me thank our Professor Dr. Pius Augustine for giving us such an opportunity to present our skills, which was only possible under his guidance. Radiocarbon dating. Let me introduce my members: Linet Sen Maria, Chetana Raut myself, Jaina J Perepadan, Deepak KV, and Sudheesh CM. We are going to deal with the topics introduction, history of radiocarbon dating, principles and different aspects, carbon exchange reservoir, and carbon dating considerations. Now, I invite Linet Sen Maria to give a brief introduction to our topic. Linet, please.
So, I would be giving you an introduction to the topic radiocarbon dating. What is radiocarbon dating? This might be a term that we had come across many times during our school days. But if we are asked to give a particular definition for this, then it would be better to define it as a technique used by the scientist to learn the ages of biological specimen. And the picture in the right side shows a specimen that was collected from an archaeological site for the purpose of radiocarbon dating. The technique radiocarbon dating was considered to be one of the most significant discoveries in the 20th century because it has helped different fields of science and is therefore referred to as radiocarbon revolution. This is the picture of Professor William Libby. He was the first one to introduce this technique and he was awarded Nobel Prize for his achievement. He did this experiment by comparing different isotopes of carbon. As we all know, an isotope is something that have same number of proton and different number of neutrons. This is an apparatus that is used during the process of radiocarbon dating. And this slide shows how a beta decay takes place and the unstable carbon isotope changes to nitrogen atom. This is the picture of Jesus Christ that we all might have come across at least once. And this is estimated to have been in the late 14th century. And it was calculated with the help of this technique. This slide shows how a carbon 14 is produced. The cosmic radiations enter the atmosphere and gets collided with the nitrogen atom. As a result of this collision, carbon 14 is produced. And this carbon 14 combines with the oxygen and carbon dioxide is formed. And this carbon dioxide is intaken by plants, animals, etc. Once a living organism dies, it stops acquiring carbon 14 from the atmosphere and the carbon 14 within its biological material starts to decay. And because of that, the ratio between carbon 14 and carbon 12 will decrease. Here, carbon 14 decays at a known rate and this helps us to determine its age accurately. As I have mentioned earlier, it has helped different fields of science and it includes hydrology, geophysics, etc. Not only that, it also had helped to prove and disapprove the theories that once existed. It had also helped in clearing out many misbeliefs that had once prevailed around us. And this may include about the origin of civilizations, etc. Radioactive decay is used as a clock because it is unaltered by the physical and the chemical changes in our environment. And the picture in the right side is a polychrome pictograph that was collected from southwest Texas. The central figure in the given picture is called as Electric Jesus, and its age is estimated to be 3000 to 4000 of years. All these discoveries were possible because of this wonderful technique, radiocarbon dating. This is the picture of an ancient Homo sapiens skull that is ever found. So, now what I have given is a glimpse idea of what we are going to discuss throughout this session. The topics that I have mentioned would be taken in detail in the coming sessions. So, I would like to invite Chetana to continue the session.
We can recall again that radiocarbon dating, also referred to as carbon dating, is a method for determining the age of an object containing organic material by using the properties of radiocarbon. Now, let's move on to our topic and see how the radiocarbon dating was discovered and how it helped archaeologists to date ancient objects. The invention of radiocarbon dating had a great impact on modern man, as radiocarbon dating was among the most significant discoveries of the 20th century, which became a topic of interest for people to know more about their history. No other scientific method had helped man to a great extent to understand not only of his present, but also of the events that already happened thousands of years ago. It is a great method to estimate the time and dates of our history. Archaeologists use the method of radiocarbon dating to prove or disprove any theories of events of history that happened long back ago. The foundation of radiocarbon dating was made by Martin Kamen and Samuel Rubin in 1939. They began experiments to determine if any of the elements common in organic matter had isotopes with half-lives long enough to be of value in biomedical research. They synthesized carbon-14 using the laboratory's cyclotron accelerator and soon discovered that this atom's half-life was far longer than had been previously thought. Willard Libby, who was then at Berkeley, conceived the idea that it might be possible to use radiocarbon for dating. Willard Libby was an American physical chemist. He had a major role in the development of radiocarbon dating in 1949. He was also been awarded with the Nobel Prize in Chemistry in 1960. In 1946, Willard Libby proposed an innovative method for dating organic materials by measuring their content of carbon-14. He published a paper in 1946 in which he proposed that the carbon in living matter might include carbon-14 as well as non-radioactive carbon. The radiocarbon revolution was only possible by Willard Libby's discovery of radiocarbon dating, which benefited in different fields of archaeology and geology, which allowed practitioners to develop more precise historical chronologies across geography and cultures. For the archaeologists, it was a great invention for the forensic proofs and also to estimate the age of rocks and fossils. Over the years, carbon-14 dating has also found its applications in varieties of fields like in geology, hydrology, geophysics, atmospheric science, oceanography, paleoclimatology, and even biomedicine. Now, I invite Jaina J Perepadan to continue the presentation.
Before coming to the next topic, that is the principle and different aspects of carbon dating, we need to know a little bit more about carbon. Carbon is indispensable to our biological life. Actually, all life on earth is based on it. And it is very familiar to us as a black substance in cardboard, as a diamond, and even it can be seen in our lead pencil that we use today. Right? So, carbon 2 comes in several forms or isotopes. Isotopes of carbon are categorized into two, and they are non radioactive and radioactive isotopes. Carbon 12 and carbon 13 belong to the first category, and carbon 14 belong to the other category. In this slide, we will be coming to know a bit more about carbon isotopes and its natural abundance. As we all know, isotopes are the one which are having same number of proton, but the varying factor is the number of neutrons present in it. Here the blue color represent the protons and a red represent neutrons. Coming to carbon 12, its natural abundance or its percentage is 98.9% and having 6 protons and 6 neutrons. In carbon 13, its percentage is 1.1 and having 6 proton as that of carbon 12 and 7 neutrons. And moving on to the very rare carbon isotope, that is the carbon 14, its natural abundance is very less and it is less than 0.1%, having 6 proton and 8 neutrons. As Chetana mentioned, radiocarbon dating, it is a method which is used to determine the age of an object that contain organic material, and carbon 14, which is the radioactive isotope, is used for this method. We come across that carbon 14 is the main thing that we use during dating. So, do you know how carbon 14 is formed? Actually, carbon 14 is formed in the upper troposphere, and it is said that when the cosmic rays from the sun enters into the atmosphere, they do commonly collide with the atoms present in the atmosphere and create secondary cosmic rays, and they are in the form of an energetic neutron. These energetic neutrons collide with the nitrogen atoms present, which is having 7 protons and 7 neutrons. Here we can see the nuclear reaction, that is the nitrogen colliding with a neutron and turns into carbon 14, the radioactive isotope, and it is having 8 neutron and 6 proton. And here we can see there is an emission of protons too. And the produced carbon 14 then combined with the oxygen and forms carbon monoxide, and on further oxidation it forms carbon dioxide. Here the reaction is shown. Carbon 14 plus O2 gives CO, the carbon monoxide, and carbon monoxide reacting with hydroxide or the OH, they do form carbon dioxide with the release of hydrogen. And the produced carbon dioxide is then diffused to the lower atmosphere and to the water bodies. The carbon dioxide is captured by the plants naturally, as we all know, through photosynthesis, and animals do get through their diet, and thereby carbon 14 is distributed all over the entire biosphere. We come across that carbon 14 is called as a radioactive isotopes. Do you know what's the reason behind it? It's because carbon 14 are very unstable, and so as to attain its stability they do undergo decay. And the equation for the radioactive decay is as shown. Carbon 14 undergoing decay comes to its initial state, that is nitrogen 14, with the emission of electron anti-neutrino. Till this much we were till this time we were seeing different bits of the entire carbon cycle, and now here it shows the sum up picture of the carbon cycle. And here we can see the cosmic rays coming from the corner to the atmosphere, and the energetic neutron do collide with nitrogen, carbon 14 is formed, they do combine with oxygen, carbon dioxide is formed, and they are captured by the living organism. As carbon 14 is very unstable, they do undergo beta decay and comes to its initial state, that is nitrogen, and the cycle continues. And this is how the whole carbon cycle works. So now let's see the principle of carbon dating. Before coming to this point, we need to know the basis of carbon dating. It is said that the radiocarbon is constantly being created in the atmosphere. So when an organism is alive, they acquire carbon 14, and the ratio between the carbon isotope carbon 14 and carbon 12 will be constant. But when the organism die, they stop acquiring carbon 14 and the ratio gradually decreases. This is because the quantity, the amount of carbon 12 will be remaining constant, but carbon 14, as they are unstable, they undergo decay and its quantity decreases gradually. So the ratio also decreases gradually. Here we said that carbon 14, the radioactive isotope, undergo decay. So the equation for a radioactive isotope decaying is as shown: N is equal to N0 e raised to minus lambda T. Here N0 is the number of atoms of the isotope in the original sample, N is the number of the atoms left after time t, and lambda, as we all know, is a constant, but they do depends upon the isotopes. And for carbon 14, it's 8267. So we do carbon dating so as to know how old a sample is, right? So in order to know that, we can just apply an equation, and the equation is thus, that is T is equal to ln nf divided by n0 whole divided by minus 0.693 into t half, where ln is the natural logarithm and nf by n0 is the percentage of carbon 14 in the sample compared to a living tissue, and t half is the half-life of carbon 14, and it's 5700 years. Here comes a question, and the question is that if a fossil had 10% of carbon 14 compared to a living sample, then calculate how old the fossil is. And it is said that it is asked it should be calculated using carbon dating. So the whole values are given, and the question is very direct. So just applying to the earlier equation, we will be getting that it's about 18,914 years old. The sample is 18,914 years old. And here comes many of us will be having some question, or one question, that why we can't carbon date a dinosaur. It's because as I told, T half of carbon 14 is about 5700 years. So by calculating T, we will be getting an approximate value that it will be about 60,000 years old. So the sample that we have to carbon date is older than 60,000 years, then if we do carbon date, the values that we are getting will not be the exact value. There will be many deflections, and thereby the calculated value will be wrong. So that's the reason why we can't carbon date dinosaurs. As we all know, they are seen very early, very earlier, and thereby we can't carbon date dinosaur and extinct species. Okay, then as carbon 14, there are other radioactive isotopes, not radiocarbon, radioactive isotopes, and they are uranium 235, uranium 238, thorium 232, rubidium 87, potassium 14, and you can see their half-life too. And these ones are also used for such purpose, other datings, sorry, not carbon dating, other datings. So that's the end of my topic. So now I invite Deepak KV to continue the session. Thank you.
Good evening to all. Today I am going to present the topic about carbon exchange reservoir. Before going to know about carbon exchange reservoir, we need to know about the carbon, which has been already explained. Carbon is the 15th most abundant element in the Earth's crust. Carbon makes up only about 0.025% of Earth's crust. The atoms of carbon can bond together in different ways, resulting in various allotropies. The main allotropies of carbon are graphite, diamond, and Buckminster fullerene. Now we are going to study how carbon is distributed in the entire universe and about the carbon exchange reservoir. Carbon is distributed through the atmosphere, biosphere, and the oceans, and these three components are fed collectively known as the carbon exchange reservoir. The reservoirs are the atmosphere, the terrestrial biosphere, which usually includes freshwater systems and non-living organic material such as soil carbon, and the oceans also, which includes dissolved inorganic carbon and living and non-living marine biota, and the sediments, which is the fossil fuels. Next is a flowchart showing about carbon exchange in various reservoirs. Here we find that different elements contain different amount of carbon. For example, atmosphere contain 1.9% of carbon, terrestrial biosphere contain 1.3% of carbon, surface ocean contains 2.4% of carbon, dead organic matter contains 3.6% of carbon, and the deep ocean contains 90.8% of carbon. Here, percentages shows the fraction of the total carbon reservoir of each type, and the numbers after slash show the ratio of carbon 14 to carbon 12, and this ratio is referred as the atmospheric ratio. Next is about the ratio and amount of carbon they store. We know that different elements contain different amount of carbon. Here we will study how they store carbon and about their carbon ratio, which is generally generated by the cosmic rays. The different elements in the carbon exchange reservoir vary in how much carbon they store and how long it takes for the carbon 14 generated by the cosmic rays. This affects the ratio to carbon 14 to carbon 12 in the different reservoirs. Next is about the atmosphere. The atmosphere, where carbon 14 is generated, contains about 1.9% of the total carbon in the reservoirs. The ratio of carbon 14 to carbon 12 in the atmosphere is taken as the baseline for other reservoirs, and this baseline is known as atmospheric baseline. If any other reservoir which has a lower ratio of carbon 14 to carbon 12, it indicates that carbon is older, and there are some carbon 14 may be decayed. Decayed carbon 14 means the reservoir is receiving the carbon that is not at the atmospheric baseline. Next is about carbon in the ocean surface. Carbon in the ocean surface contains 2.4% of carbon in exchange reservoir. the time it takes for carbon from the atmosphere to mix with the surface ocean is only a few years. The surface water also receives water from the deep oceans, which has more than 90% of carbon in the reservoir. Water in the deep oceans takes about thousands of years to circulate back through surface water. Next is about the carbon ratio in different organisms, especially the creatures living at the ocean surface, the plants and animals, and the living and non-living organisms. It says that creatures living at the ocean surface have the same carbon-14 ratios. The radiocarbon age of marine life is about 400 years. Carbon stored in living organisms is called biomass carbon and is found in all marine vertebrates. Large animals such as whales can store large quantities of carbon for long periods of time. Organisms on land are in closer equilibrium with the atmosphere and have the same carbon 14 to carbon 12 ratio as that of the atmosphere. These organisms contains about 1.3% of carbon in the reservoir, which is already explained in the above flowchart. Next is about the sea organisms. It have a mass of less than 1% of carbon. Accumulated dead organic matter, both plants and animals, exceeds the mass of the biosphere. But this matter is no longer exchanging carbon with the environment. So it has a lower ratio than that of the atmosphere. Thank you. Next I call upon my friend Sudheesh to present his topic.
I am going to deal with the dating considerations. Dating considerations means the variation in the C14 by C12 ratio in different parts of a carbon exchange reservoir means that a straightforward calculation of the age of the sample based on the amount of radiocarbon it contains will give an incorrect result. There are several other possible sources that we needed to be considered. The error are of four types. Mainly variation in the ratio in the atmosphere both geographically over the time, isotopic fractionation, contamination ratio in different parts of the reservoir, etc. Okay. Next I am going to the details of isotopic fractionation. Isotopic fractionation means first we think about photosynthesis. Photosynthesis is the primary process by which carbon moves from the atmosphere into living things. In photosynthetic pathway, C12 is more absorbed slightly more than C13, which then is more easily absorbed than C14. C14 means radiocarbon. The differential uptake of the three carbon isotopes led to the ratio of C13 by C12 and C14 by C12 in plants that differ from the ratios in the atmosphere. This effect is known as isotopic fractionation. Okay, understand? To determine the degree of fractionation, there is an equation. It is the ratio C13 by C12 of the sample divided by C13 by C12 of standard form. This minus 1 into 1000. This equation will give the degree of fractionation. Next is reservoir effects. Reservoir effects means Libby's original exchange reservoir is hypothesis assume that C14 by C12 ratio in the exchange reservoirs is constant all over the world, but it has since been discovered that there are several causes of the variation ratios across the reservoir. This is called reservoir effect. And then next is marine effects. The carbon dioxide in the atmosphere transferred to the ocean, dissolving in the surface as carbonate and bicarbonate. We already know that. Okay, then these to the at the same time of the carbonate ions in the water are returning into the air as carbon dioxide. This exchange process brings radiocarbon from the atmosphere into the surface of water of the ocean, but radiocarbon thus introduced takes a long time to percolate through the entire volume of the ocean. The deepest part of the ocean mixes very slowly with the surface of water, and mixing is uneven. Not even, it is uneven. The main mechanism bringing the water to surface is upwelling, which is more common in the region closer to the equator. This is marine effect. Okay. Next is hemisphere effect. Northern and southern hemisphere having atmospheric circulation system that are sufficiently independent of each other. There is a noticeable time lag in the mixing between the two. Atmospheric C14 by C12. C14 is radiocarbon. This ratio is lower in the southern hemisphere with an apparent additional age about 14 years of radiocarbon result in the south compared to the north. This is because of greater surface area in the ocean in the southern hemisphere. Means there is more carbon exchange between ocean and atmosphere in the north. This is hemisphere effect. Okay. Next, other effect which include the carbon in fresh water is partly acquired from the aged carbon. Okay, for example, limestone, which calcium carbonate, etc. Hard water is formed because of the calcium carbonate or magnesium carbonate, etc. By dissolving that into the water, then hard water. The hard water also cause some effect in and volcanic eruptions. Volcanic eruptions in the volcanic eruptions means that it add carbon to the atmosphere, which cause increasing the radiocarbon or that cause some errors in the calculation. Okay. Next is contaminations. Contamination of modern carbon to a sample which make the appear younger than reality. That is mixing up of modern carbon with the sample. Sample contain old carbon. Then mixing of these give an incorrect result, which appear that the sample become young. Okay. Thank you.
Now, our presentation comes to an end. We hope that our presentation was informative and all of you might have got some idea about the topic. On behalf of my group members, I would like to express my sincere gratitude to Professor Dr. Pius Augustine and also to the audience for your keen listening and spending your time for us. Thank you.